4.8, and then, 3 days, 9 hours and 33 minutes later, 4.8 again, the same magnitude to the decimal on the same patch of ground beneath the southern edge of Granada. For 3 days, that sequence had been dying down exactly the way seismologists want a sequence to die down. Then it produced its own twin, followed by a 3.9, a 4.2, and a 4.0 inside 2 hours. 600 people are out of their homes, the Alhambra is shut, and for the first time scientists have the diagrams that show how the rock is actually breaking down there. And what those diagrams raise is far worse than a bigger number. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs, and leave a comment with where you're tuning in from tonight. Now let's break this down. Part 1. The second one was exactly the same size. At 37 minutes past 10 on Tuesday morning, in a town called Gojar on the southern edge of the Granada metropolitan area, the ground moved. It was not the first time that week. It was not even the 10th time that week. But this one was different from the dozens of small tremors that had rolled through the valley over the previous 3 days, and it was different in a way that took seismologists most of the afternoon to fully appreciate. It was exactly the same size as the one that started all of this. I want to give you the two numbers straight away, because everything in this video hangs off them, and I do not want you sitting through 20 minutes of build-up before you understand what the actual problem is. On the 14th of August, at 4 minutes past 11 at night in Coordinated Universal Time, an earthquake struck near the town of Alhambra, just south of the city of Granada. Spain's National Seismic Authority, the Instituto Geográfico Nacional, measured it at moment magnitude 4.8. Then, on the 18th of August, at 37 minutes and 45 seconds past 8 in the morning, Coordinated Universal Time, another earthquake struck the same small patch of ground. The same institute measured that one at moment magnitude 4.8. 3 days, 9 hours and 33 minutes apart. Same place, same size, to the decimal. Now here is why that is the alarming detail rather than the reassuring one, and I want to be careful about this because the instinct runs the wrong way. When people hear that the second earthquake was not bigger than the first, they relax. It did not escalate. It did not climb. Nothing got worse. And in one narrow sense that is true, and I will come back to it later because it genuinely matters. But a main shock aftershock sequence, which is the thing everybody assumed this was, has exactly one dominant event. That is not a rule of thumb. That is the definition. One rupture releases most of the accumulated stress, and everything that follows is the surrounding rock adjusting to a new arrangement, which is why aftershocks get smaller and less frequent over time, in a way that is predictable enough to have its own equations. The largest aftershock in a typical sequence sits roughly 1 and a bit magnitude units below the main shock. There is a hierarchy, and the hierarchy is the whole point. This sequence now has 2 events at the top, which means it does not have one. That is the change, not the magnitude, the structure. For 3 days, everything looked like it was ending. After the 14th of August, the sequence did what sequences are supposed to do. The aftershocks came, and they got smaller, and the largest of them slid down into the magnitude 1 and magnitude 2 range, and the interval between the ones people could actually feel got longer. Anybody watching the feed on the 17th of August would have told you correctly that this was a sequence in decay. The valley was quieting down. That is not a comforting interpretation applied in hindsight. That is what the data was showing, and then on Tuesday morning it produced its own twin. Let me deal with the 2 reactions that people are having to this, because they are both wrong and they are wrong in opposite directions. The first reaction is that the earthquakes are ramping up towards something enormous, that this is the pattern that precedes a catastrophe, and that Granada is about to be hit by something historic. There is nothing in the current data that supports that. I will show you exactly why later, and I will show you what the numbers would have to look like for that reading to have any weight behind it. They do not look like that. The second reaction is that this is fine. It is just aftershocks. Moderate earthquakes happen in southern Spain. Move along. That reading is also wrong, and it is wrong in a way that has already put 600 people out of their homes. The real question is neither of those. The real question is, what is controlling the sequence? Because for 3 days there was an obvious answer. The earthquake on the 14th of August was controlling it, and everything else was a consequence. As of Tuesday morning, that answer no longer works, and nobody has a replacement for it yet. There is a detail in the raw data that makes all of this considerably worse, and it has nothing to do with magnitude at all. Every single located earthquake in this series has been shallower than 10 kilometers. The Institute's own bulletin uses the phrase muy superficiales, very superficial, for the largest of them. Depth is the parameter that people ignore, and it is the parameter that decides how an earthquake feels. Seismic energy spreads out as it travels, which means it thins out. An earthquake at 100 kilometers depth has to push its energy through 100 kilometers of rock before any of it reaches a person standing on the surface, and by the time it gets there, it has spread across an enormous volume and lost most of its punch. That is why a magnitude 6 at 400 kilometers depth can be barely felt, while a magnitude 4 at 2 kilometers depth can throw objects off shelves. These earthquakes are happening close enough to the surface that, for the people directly above them, a magnitude 4.8 behaves like a much larger earthquake somewhere else. Not because it is releasing more energy, because none of the energy has anywhere to go, and there is nobody directly above them in the sense of an empty hillside. The epicenters sit between 2 and 12 kilometers south of the city of Granada, under the towns of Alhambra, Gojar, and La Zubia. This is not a remote fault in a mountain range. This is a commuter belt. It is farmland turning into apartment blocks, turning into a city of 250,000 people, and the earthquakes are happening underneath the part where the apartment blocks are. So let me tell you what Tuesday actually looked like on the surface, because the response tells you how seriously the people whose job it is to make these calls are taking it. The Alhambra closed. The Nasrid palaces and the Alcazaba were evacuated and visits were suspended. One of the most visited monuments in Spain, a structure that has stood through 6 centuries of earthquakes in a basin that produces them regularly, was cleared of people and shut on a Tuesday morning because of a magnitude 4.8. Shopping centres across the metropolitan area were evacuated. Heritage buildings were inspected. The Granada metro dropped its operating speed to 30 kilometers an hour, which is the kind of decision you make when you're not confident about the track bed and you would rather find out slowly. And in the town of Las Caballas, engineers ordered the evacuation of 371 homes across 6 apartment blocks, roughly 600 people. I want to be precise about that number, because it is the one that gets misread most often. Those 600 people are not out of their homes because they are frightened. Frightened people sleep in their cars for one night and go back inside in the morning. These are organised evacuations, ordered by engineers, after inspections found conditions in those buildings that require detailed structural analysis before anybody is allowed to return. The town opened its municipal theatre for residents who had nowhere else to go. 3 people were injured, all of them minor injuries, one of them a young miner taken to hospital. Emergency line 112 in Andalusia took more than 50 calls reporting collapses and cracking, and the detail that tells you the most about how the previous 4 days had already worn on the valley. The town opened not just the theatre but public spaces, parks, football grounds, for people who did not want to spend the night under a roof they no longer trusted. That is not an evacuation order. Nobody told those people to leave. They looked at their own ceiling and made a decision, and the town made room for them. That is the human scale of this, and I am going to be straight with you about it throughout. This is not a mass casualty disaster, and I am not going to pretend it is one. Nobody has died. The injuries are minor. What is happening in Granada right now is not a catastrophe. It is something stranger and, in a way that I think is genuinely more interesting, harder to read. Because on Tuesday afternoon, the Institute got hold of something it did not have on the 15th of August. Something that does not tell you how big an earthquake was, or where it was, but tells you how the rock actually broke. And the moment that information arrived, the question everybody had been asking stopped being the right question. For 3 days this looked like a story that was ending. Then it produced its own twin, and now nobody is sure whose story it is anymore. Part 2. 432. 432. That is the number of earthquakes the Instituto Geográfico Nacional has located in this sequence since midnight on the 14th of August. Not estimated. Not detected as a smear of energy on a seismogram. Located, meaning each one has been assigned a position, a depth, a time and a magnitude, and each one has been reviewed. 432 in 5 days, under an area you could drive across in 15 minutes. The shape of that catalogue matters more than the total. The overwhelming majority of those events are below magnitude 2, which means most of them were never felt by anybody, and exist only as wiggles on an instrument. 9 of them reached magnitude 3 or above. 45 were felt by the population, so the ratio is roughly 1 in 10. For every 10 earthquakes the network locates under the Vega de Granada, one of them registers as an experience for a human being rather than a data point. Now, the 432 figure is the located catalogue, and I want to be clear about what that does and does not include, because this is a place where numbers get inflated in the retelling. Regional seismic networks operating at lower detection thresholds pick up substantially more than the national located catalogue does. A dense local array with instruments sitting a few kilometres from the source can resolve events down below magnitude 0. Earthquakes with less energy than a truck going over a pothole, which never reached the surface as anything a person could detect, and which nobody would call an earthquake in ordinary conversation. So when you hear that there have been thousands of signals under this basin, that is not a contradiction of the 432 figure. It is a different measurement using a different threshold. The national catalogue is the conservative, reviewed, located number. The lower threshold count is a measure of how much the rock down there is creaking. Both are real. Only one of them is comparable to catalogues from other sequences. Here is a number that I find genuinely striking, and it is not a seismological measurement at all. Since the 14th of August, the Institute has received more than 15,000 macroseismic questionnaires through its website and its mobile app. A macroseismic questionnaire is a form that a member of the public fills in after they feel an earthquake. Where were you? What floor? Did objects move? Did anything fall? Did you hear it before you felt it? Was it difficult to stand? It sounds like a comment box, and it is not. It is a data collection instrument, and the answers are converted into intensity values on a formal scale, which are then mapped. That matters because seismometers measure ground motion at the specific points where seismometers happen to be installed. There are 52 of them in a 50-kilometre radius here, which is a lot, but there are hundreds of thousands of people. The questionnaires fill in the space between the instruments. They are how you find out that shaking was severe on one side of a town and mild on the other, which is exactly the kind of detail that reveals how local geology is amplifying or damping the waves. 15,000 of them in 5 days is a very large sample, and it produced a result that surprised people. Both magnitude 4.8 events were felt in more than 500 localities, central and eastern Andalusia, obviously, but also parts of the region of Murcia, southern Castilla-La Mancha, and the community of Madrid. Madrid is roughly 350 kilometres from Alhambra. For a magnitude 4.8, that is a remarkable felt footprint, and there are 2 reasons for it working together. The first is the shallowness we already covered. The energy starts near the surface, so more of it stays near the surface and travels laterally through the crust, rather than radiating downward and outward through the mantle. The second is the ground it travels through. Seismic waves passing from hard rock into soft sedimentary basin slow down, and when a wave slows down it has to grow in amplitude to conserve energy. Sedimentary basins act like acoustic lenses. The Iberian Peninsula is not one uniform block of granite. It is a mosaic of basins and massifs, and a wave that happens to travel along a path with the right sedimentary structures at the far end can arrive somewhere distant with more amplitude than the distance alone would predict. People on the upper floors of tall buildings in Madrid felt a sequence of earthquakes 350 kilometres away, on the 5th floor of a building that was doing its own slow sway in response. The maximum observed intensity for both large events was 5 to 6 on the European macroseismic scale. Let me translate that, because intensity and magnitude are constantly confused, and the difference is the difference between describing an earthquake and describing what an earthquake did to you. Magnitude is a property of the earthquake. One earthquake, one magnitude, calculated from the energy the rupture radiated. It does not matter where you are standing. Intensity is a property of a place. It describes effects, what people felt, what objects did, what buildings did, at a specific location, which means one earthquake produces a whole map of different intensity values, high near the source and falling away with distance. Intensity 5 is where an earthquake stops being a curiosity. It is felt by almost everybody indoors. Many people are woken, small objects fall over, doors swing, hanging objects swing noticeably, and there is often audible noise from the building itself. Intensity 6 is where damage starts appearing. Cracks in plaster, small pieces of masonry falling, objects thrown from shelves rather than tipped over, and people running outdoors. 5 to 6 is the band where an earthquake stops being an event you talk about and becomes an event that leaves marks on the walls. Both of these earthquakes reached it, in populated areas, 4 days apart. And there were warnings, in the sense that there were earthquakes beforehand, although calling them warnings is only possible now, looking backward. On the 14th of August at 43 minutes past 4 in the afternoon, Coordinated Universal Time, a magnitude 3.7 struck about 4 kilometers northeast of where the first 4.8 would strike roughly 6 hours later. It reached intensity 4. People felt it. And 3 weeks before any of this, on the 26th of July, a magnitude 3.6 occurred southwest of Armilla. Also very shallow. Also in the same neighbourhood of the Basin. It is tempting to look at that and see a staircase. 3.6 in July, 3.7 in the afternoon, 4.86 hours later. A building sequence, a fault clearing its throat. I need to be honest with you about why that reading is a trap, and it is one of the most important things in this entire video. Foreshocks are only ever foreshocks in retrospect. There is no physical property that distinguishes a magnitude 3.7 that will be followed by a larger earthquake from a magnitude 3.7 that will be followed by nothing at all. They look the same on the instrument. They have the same mechanisms, the same durations, the same frequency content. The label foreshock is applied afterward, by the arrival of something bigger, and it cannot be applied in advance, and the base rate is brutal. The overwhelming majority of magnitude 3.7s anywhere on Earth are followed by absolutely nothing. In a seismically active basin like this one, magnitude 3-point-somethings are routine. If you evacuated a city every time one occurred, you would evacuate it several times a year, forever, and you would be wrong essentially every time. So no, nobody missed a warning on the 14th of August. There was no warning to miss. That is not a failure of the monitoring system. It is a limit of the physics. The honest version of what foreshocks give you is statistical, and it is thin. Across large global catalogues, something in the region of 5 to 10% of moderate earthquakes turn out to have been followed by a larger event within a few days, which means 90 to 95% of the time, the small earthquake was just a small earthquake. Those are not odds you can act on. They are odds you can study. What the 26th of July event does give you, in hindsight, is a hint that this patch of crust had been under increasing strain for at least 3 weeks before anybody noticed. That is not predictive. It is contextual. It tells you the process that produced the 14th of August did not begin on the 14th of August, which means none of these numbers, not 432, not 15,000 questionnaires, not 500 localities, not intensity 6, actually tells you what shape this sequence has. They tell you how much is happening and how it feels. For the shape, you need to look at what happened in a single 2-hour window on Tuesday morning. Part 3. 2 hours on a Tuesday morning. 8:37 and 45 seconds, Coordinated Universal Time, 25 to 11 in the morning local time in Granada, moment magnitude 4.8, epicenter in the vicinity of Alhambra, reported through most Spanish coverage as centered on Gojar, which sits directly adjacent. Maximum observed intensity 5 to 6. Very shallow. That is the event that reset this entire story. But it is what happened over the following 2 hours that tells you the sequence has changed shape, and I want to walk you through it in order, because the order is the argument. 8:53 and 9 seconds. Moment magnitude 3.9, located south of Churiana de la Vega. That is 15 minutes and 24 seconds after the main event. 9:34 and 37 seconds. Moment magnitude 4.2, located north of Alhambra. 57 minutes after the main event. 10:39 and 44 seconds. Moment magnitude 4.0, located northeast of Gojar. 2 hours and 2 minutes after the main event. So inside a window of roughly 2 hours, this relatively small volume of crust produced a 4.8, a 3.9, a 4.2 and a 4.0. Spanish reporting counted something like 20 earthquakes in a little over 2 hours across the metropolitan area, with epicenters scattered across different municipalities. Look at those 4 locations again, because this is a detail that gets lost when people only look at the magnitudes. Near Alhambra, south of Churiana de la Vega, north of Alhambra, northeast of Gojar. They are not stacking on a single point. They are distributed across a few kilometers of the valley floor in different directions from each other. That does not on its own prove anything. Aftershocks routinely spread across the area surrounding a rupture, and a rupture itself is a surface with dimensions rather than a point. but it is not the tight concentric pattern you would draw if you were sketching a textbook example. Now compare Tuesday to the 14th of August. After the first 4.8, the sequence produced aftershocks that got smaller. Not immediately, not perfectly, but the trend was unmistakable and it held for 3 days. The largest events slid down into magnitude 1 and 2 territory. The felt reports thinned out. It looked like the standard picture. One big release, and then the rock around it settling into a new arrangement through a long series of progressively smaller adjustments. After the second 4.8, the sequence produced a 3.9, a 4.2, and a 4.0 inside 2 hours. That is not a decaying tail. That is a fault volume that is still finding things to break. There is a rule of thumb in seismology that is old enough to have a name attached to it, and it is worth knowing because it gives you a yardstick. In a typical main shock aftershock sequence, the largest aftershock tends to come in around 1.2 magnitude units below the main shock. It is not a law of physics. It is an empirical regularity, and individual sequences scatter around it in both directions. But it holds well enough across enough sequences that seismologists use it as a first expectation. Apply it here. A magnitude 4.8 main shock should, on that expectation, produce a largest aftershock somewhere around magnitude 3.6. The sequence on the 14th of August behaved reasonably close to that. The sequence on the 18th of August produced a second 4.8. A largest aftershock that equals the main shock is not an aftershock in any useful sense of the word. It is a second main shock, and the vocabulary breaks down at that point, which is exactly why seismologists stop talking about aftershocks and start talking about sequences. There is a second empirical relationship worth having in your head, because it is the one that makes the 3 quiet days meaningful. Aftershock rates decay in a very particular way, not linearly, but roughly as 1 over elapsed time. The rate is highest in the first hours, drops fast over the first day, and then trails off slowly for weeks or months. It is why the first 24 hours after any significant earthquake are the dangerous ones for damaged buildings, and it is why a sequence that has been quiet for 3 days is usually a sequence that is genuinely winding down rather than one that is pausing. That decay curve is the reason the 17th of August looked like the end of the story. The rock was doing exactly what the equation says it should, and then it stopped following the equation. I want to walk you through what those 2 hours actually meant for somebody standing in Las Caballas or Armilla or Otura, because the timestamps flatten the experience. The first one, at 25 to 11, is the one that empties buildings. Intensity 5 to 6 means people do not walk out, they leave. Objects come off shelves, plaster cracks. There is a noise that arrives fractionally before the shaking. A low rumble as the faster compressional wave outruns the slower shear wave that carries most of the destructive motion. In a shallow earthquake, the gap between them is a second or less, which is enough time to register that something is coming and not enough time to do anything about it. 15 minutes later, while people are still standing in the street, the ground does it again. 3.9. Smaller, but everybody's outdoors and paying attention now, and a 3.9 at that depth is unmistakable. Then a 40-minute gap, which is long enough for some people to go back inside. Then, at 10:30 in the morning, a 4.2. That is the one that sends everybody back out and keeps them out. Then another hour of nothing, and then a 4.0. That is the pattern that turns an earthquake into a crisis. Not the size of any individual event, but the refusal of the sequence to settle into a rhythm that lets anybody make a decision. You cannot inspect a building that is still being shaken. You cannot let people back into apartments when you do not know whether the next one arrives in 3 minutes or 3 days. Here is the physical difference in plain terms. When a patch of a fault ruptures, it does 2 things at once. It releases the stress that was stored on that patch, and it changes the stress on everything around it, increasing it in some places, decreasing it in others. Aftershocks are the surrounding rock responding to that redistribution, and the reason they decay is that the redistribution is a one-time event. The stress change happened at the moment of rupture. Everything after that is the system converging on a new equilibrium, and convergence means getting smaller. When the events do not get smaller, and when a second event arrives at the same size as the first, it means one of 2 things. Either the system has not converged because there was far more stored stress in that volume than one rupture could release, or something new has entered the picture. I mentioned this sequence 4 days ago, in the video on the global earthquake rate. At the time, Granada was one line in a much bigger picture, a magnitude 5.2 in southern Spain, filed alongside the 1884 earthquake that everybody brings up whenever Andalusia shakes, one item in a global count. It was a footnote. It is now the story, and the thing that turned it from a footnote into a story is not that it got bigger, it is that it repeated. Let me put the aftershock magnitudes in perspective, because only a 4.2 is a phrase that does a lot of damage. The moment magnitude scale is logarithmic in a way that punishes intuition. Every full step up multiplies the radiated energy by roughly 32. A 4.2 releases about 1/8 the energy of a 4.8. That sounds like a large gap, and in absolute terms it is. But energy released at the source is not the same as energy delivered to your building. These earthquakes are happening 2 to 12 kilometers beneath towns. A magnitude 4.2 at that depth, directly under a masonry apartment block, delivers ground motion that a magnitude 5 at 50 kilometers depth would not come close to. The distance from the source to the structure is doing as much work in that equation as the magnitude is, and here the distance is essentially zero, which is how a town ends up with 4 earthquakes of magnitude 3.9 and above in 2 hours, and buildings that were already cracked getting hit 4 more times before lunch. By Tuesday afternoon, the Institute had something it had not had on the 15th of August. Enough events, with clean enough waveforms, recorded on enough instruments to compute a specific kind of solution, and that solution changed the question everybody had been asking. Part 4. The Beach Balls. The most important thing to come out of the 18th of August was not a magnitude. It was a diagram, a set of circles, each one divided into 4 segments, 2 shaded and 2 white, arranged in a pattern that looks like a beach ball. There is no number attached to them that will ever make a headline. They are the reason this story stopped being about how big the earthquakes were and started being about what is actually down there. Let me explain what they are, because once you understand these, you understand the rest of this video. When an earthquake happens, the rock does not just shake, it moves in a specific direction along a specific surface. One block of crust slides past, over or away from another block. Every seismometer that records the earthquake sees the very first arrival of that motion, and crucially, it sees whether the ground at that station moved first toward the earthquake or away from it. That first motion is called the polarity, and it is a yes or no answer. Now imagine you have dozens of stations surrounding an earthquake, at different distances and different directions. Some of them recorded a first motion pushing outward, some recorded a first motion pulling inward. Plot all of those on a sphere around the earthquake's hypercenter, and the pushes and the pulls sort themselves into 4 quadrants. 2 quadrants of compression, 2 of dilatation, alternating. Shade the compressional quadrants. You get a beach ball. The pattern of that beach ball is a direct picture of the geometry of the fault that moved and the direction it moved in. Not where it moved, how it moved. And there is a limitation built into it that turns out to be central to this entire story, so I want to flag it now rather than later. A beach ball gives you 2 planes, not 1. The 4 quadrants are separated by 2 great circles, and both of them are geometrically valid solutions. One of them is the actual fault that ruptured. The other is what is called the auxiliary plane, a mathematical ghost, perpendicular to the real one, that produces an identical radiation pattern. The seismogram cannot tell you which is which. The physics genuinely does not distinguish them. From the waveforms alone, a fault dipping steeply to the northwest and a fault dipping shallowly to the southeast are the same answer. So how do you resolve it? You do not resolve it from one earthquake. You resolve it from many. If you have hundreds of earthquakes in the same volume, and you can locate them precisely enough, they will trace out the actual surface they are occurring on, and that surface will match one of the 2 candidate planes and not the other. The cloud of hypocenters is what picks the real fault out of the pair. Hold on to that, because it is the mechanism by which the central question in this video gets answered. Modern practice goes further than first motions and computes a full seismic moment tensor, which uses the entire recorded waveform rather than just the first wiggle. The moment tensor gives you the fault geometry, the slip direction, and a size estimate, moment magnitude, which is a far more physically meaningful measurement of an earthquake's size than the older local magnitude scales, because it is derived from the actual physics of the rupture rather than from the amplitude of a needle on a drum. There are 3 basic families of mechanism, and you can do all 3 with your hands. Put your palms together flat, horizontal, one on top of the other. Slide the top hand toward you while it also drops down. That is normal faulting. It happens where the crust is being pulled apart and the block above the fault plane, the hanging wall, moves downward relative to the block below it. Now slide the top hand away from you while it rides up. That is reverse, or thrust, faulting. That happens where the crust is being squeezed and the hanging wall rides up over the footwall. This is the mechanism of subduction zone megathrusts in the largest earthquakes on Earth. Now put your palms together vertically, like you're about to clap, and slide one past the other horizontally. That is strike slip. The San Andreas is the famous one. The mechanism tells you what the crust in that region is doing at a fundamental level, because faults do not choose their own style. They respond to the stress field they sit in. So here is what the Institute found. It computed moment tensors for the largest events of the 14th of August, the magnitude 3.7 and the magnitude 4.8, and for the largest events of the 18th of August, the whole cluster from the 3.9 up to the 4.8. Every one of them shows normal faulting. Now, the word normal is doing something unhelpful in that sentence, and I want to get it out of the way immediately, because I know how it reads. Normal does not mean ordinary. It does not mean expected. It does not mean nothing to worry about. It is a piece of 19th century mining terminology that stuck, and it describes a specific geometry. Hanging wall dropping down relative to footwall, driven by extension. A normal faulting earthquake can kill tens of thousands of people. The mechanism says nothing whatsoever about danger. It says what direction the rock moved. There is one genuinely useful thing the mechanism tells you about scale, though, and it cuts in a reassuring direction, so I will give it to you honestly. Normal faults, as a class, do not produce the largest earthquakes on the planet. The physics is straightforward. In extension, gravity is helping the block move, which means less stress has to accumulate before failure, which means less energy is stored to release. The truly enormous earthquakes, the magnitude 8s and 9s, happen almost exclusively on subduction megathrusts, where an entire plate boundary is being forced downward against friction over hundreds of kilometers of contact. A continental normal fault of the kind mapped in the Granada Basin has an upper bound set by its own dimensions, and those dimensions are modest. That is a real constraint, and it is one of the reasons the honour ceiling in this basin is a magnitude 6 something rather than a magnitude 8 something. It does not mean nothing bad can happen here. 1884 settles that argument. It means the worst case has a shape, and the shape is not open-ended. What it does tell you is that the earthquakes are consistent with the mapped active faults in the area, and with the tectonics of the region. That sounds like a bureaucratic sentence, and it is actually a significant statement. It means these earthquakes are not anomalous. They are not doing something the regional stress field would not predict. Whatever is happening down there, it is happening on structures that geologists already know about, in the direction those structures are already known to move. And then there is the second half of the finding, which is the part that made everybody sit up. The Institute places this seismic series geometrically between three mapped fault structures, the Dilla Fault to the south, the Granada Fault to the east, and the Belisena-Alhambra Fault to the west. I need to be extremely careful with what that sentence means, because it is the single easiest thing in this story to overread, and it has been overread enormously online in the last 24 hours. The Institute is not saying that any of those three faults has begun rupturing along its length. It has not said that. It does not imply it. There is no evidence of a rupture racing across the Granada Basin, and nobody with access to the data has suggested there is. The statement is a spatial framing. It tells you where the seismicity sits, inside a block bounded by three known active structures. That is a description of an address, not a diagnosis. It is worth understanding what those three names actually refer to, because fault in casual usage suggests a crack, and that is not what these are. A mapped active fault in a database like the one Spanish geologists maintain is a structure that has been identified in the field or in subsurface data, traced across a known length, and demonstrated to have moved during the Quaternary, the last 2.5 million years or so. That is the threshold for active in this context. Not moving right now, moving on a geological timescale recent enough that it should be assumed capable of moving again. The Dilla Fault, the Granada Fault, and the Belisena-Alhambra Fault are three such structures, and they enclose the block of crust where these earthquakes are happening. They are the edges of the container. What has been rupturing over the last 5 days is something inside that container, and the whole question is whether inside means a single structure in the middle of it, or whether the sequence has started interacting with one of the walls. But it is a very informative address. Because now you know two things you did not know on the 15th of August. You know how the rock is breaking, normal faulting, extension, hanging wall dropping. And you know that the volume where it is breaking is bounded by 3 mapped structures, any of which is capable of a great deal more than what has happened so far. Put those two facts together with the sequence's new shape, 2 co-equal earthquakes instead of 1 dominant one, and you arrive at a question that nobody could have asked 5 days ago. The mechanisms tell you how the rock is breaking. They do not yet tell you what it is breaking on. Is every one of these 432 earthquakes defining a single fault plane, one structure failing in pieces? Or are they starting to define more than one? That is the question the next several days will answer, and the answer will not arrive as a magnitude. Part 5. A basin being pulled apart. Inside, a collision. Africa is pushing into Europe, and the ground under Granada is being stretched. Those two sentences look like they cannot both be true, and the fact that they are is the key to everything happening in that valley right now. Start with the plates. The Nubian plate, which carries most of the African continent, and the Eurasian plate, which carries Iberia, are converging. In the Vega de Granada, that convergence runs at roughly 4 to 5 millimeters per year. 4 millimeters. That is the thickness of a stack of 4 credit cards. Per year. It is a rate so slow that it is difficult to take seriously as a source of violence. A fingernail grows about 10 times faster. But geology does not work in years, and this is the number that reframes it. 4 millimeters a year is 4 meters per 1,000 years. It is 4 kilometers per million years. The convergence between Africa and Europe has been running, in various configurations, for tens of millions of years, and in that time it has closed an ocean. The Mediterranean is what is left of a much larger sea called the Tethys, and the mountains that run along the southern edge of Spain, the Beticus, are the crumpled edge of the collision that consumed it. So the region is being squeezed, and yet the earthquakes under Granada are normal faulting, which is the mechanism of extension. Here is why, and it is one of the more counterintuitive results in continental tectonics. When you squeeze a mountain range, you thicken the crust. The rock has nowhere to go but up and down, up into topography, and down into a thickened root beneath the range. That thickened crust is heavier than the crust around it, and it is sitting on a mantle that behaves, over geological time, like an extremely viscous fluid. Now think about what happens to a pile of wet sand when you keep pushing sand into the middle of it. The pile grows, and it steepens, and at some point the sides of the pile start to slump outward under their own weight, even though you are still pushing sand into the middle. The pile is being fed by compression, and it is failing by extension, simultaneously in different parts of the same structure. That is what the interior of the Betic Cordillera is doing. The mountain belt as a whole is being shortened by the plate convergence, and at the same time the thickened, over-steepened interior is collapsing under gravity, pulling itself apart in the middle. Geologists call it gravitational collapse or orogenic extension, and it produces exactly what you see here, a compressional plate boundary with an extending, subsiding basin sitting inside it. The Granada Basin is that subsiding interior. It is a depression bounded by normal faults, filling steadily with sediment eroded off the mountains around it, and dropping relative to those mountains as the faults on its edges slip. The valley floor that the towns of Alhambra and Gojar and Las Gabias are built on is not bedrock. It is basin fill, sands, gravels, clays, hundreds of meters of it in places, laid down over millions of years. There is a second engine involved as well, operating underneath the first, and it explains why the extension here is as vigorous as it is. Beneath the Alhambra Sea, the western Mediterranean between Spain and Morocco, there is a fragment of oceanic lithosphere that was dragged down as the Tethys closed, and which has been peeling backward and downward through the mantle for millions of years. As that slab retreats, it drags the crust above it outward, the way a rug is pulled from underneath you. The Betic and Rif mountains curl around the Alhambra Basin in a tight arc, and that arc is the fingerprint of a slab that rolled back and stretched the crust behind it, while the plates themselves kept converging. That is the deeper answer to why the ground under Granada is being pulled apart during a continental collision. Something is pulling on it from below. There is also shortening in the region, running at roughly 2 millimeters a year on structures like the Sierra de Alhambra antiform to the southwest. Both signals coexist in the same landscape. Extension in the basin interiors, shortening on specific structures at the margins. It is a complicated stress field, and complicated stress fields produce a lot of faults in a lot of orientations, which is why the geological map of this region looks like a dropped plate. That sediment fill matters twice over, and both times against the people living on it. The first is amplification. Seismic waves travelling through hard bedrock move fast. When they enter soft sediment, they slow down, and because energy has to be conserved, slowing down means growing in amplitude. A basin full of loose sediment does to seismic waves roughly what a megaphone does to a voice. Worse, basins can trap waves. Energy bounces around inside the sedimentary layer instead of passing through, which stretches the duration of shaking. A 3-second pulse arriving at bedrock can become 15 seconds of shaking on the basin floor above it. The second is that basin fill is why anybody lives there. Flat ground, deep soil, water. The Vega de Granada is agricultural land that has been farmed continuously for over 1,000 years and built on heavily in the last 50. The same geological process that makes the ground shake harder is the process that made the ground worth settling. And there is a cruel geometry to how that plays out across a city. Granada itself sits partly on the higher ground at the edge of the basin, on firmer material. The Alhambra sits on a ridge, the Sabika Hill above the valley floor. The towns that took the worst of Tuesday morning, the ones with the evacuated apartment blocks, sit out on the flat, on the deep fill where amplification is strongest. So the shaking a person experienced on Tuesday depended less on how far they were from the epicenter than on what their building happened to be standing on. Two towns the same distance from the source, one on gravel over bedrock and one on hundreds of meters of soft sediment, will report completely different earthquakes. That is not an anomaly in the data. That is the data working correctly, and it is why 15,000 questionnaires from ordinary people are scientifically valuable rather than merely interesting. Now, the Institute's own assessment of this region is not ambiguous, and I want to read the sense of it plainly. The Granada Basin, in the central sector of the eastern Beticus, is among the zones of greatest seismic activity and greatest seismic hazard on the entire Iberian Peninsula. Which brings me to a framing that ran through a lot of international coverage after the 14th of August, and which is simply factually wrong. The framing was that Granada is an unusual place for a significant earthquake, that southern Spain is not really earthquake country, that this was a freak event in a quiet corner of Europe. Let me give you the receipts on that, because it is worth correcting properly. This basin produced a catastrophe in 1884 that killed close to 1,000 people. It produced an earthquake in 1431 that reached intensity 8 to 9. It produced series reaching intensity 7 and 8 in 1806 and 1807 at Pinos Puente, in 1911 at Santa Fe, and in 1918 at Atafe. It produced magnitude 5 earthquakes at Armilla in 1955 and at Purchil in 1956, both of them inside what is now the metropolitan footprint of the city. And between December of 2020 and August of 2021, it produced a sequence of more than 3,000 earthquakes about 10 kilometers northwest of where the current one is happening. Nothing about this location is rare. This is one of the most seismically active places in Western Europe, and it has been described that way by the people who monitor it for as long as anybody has been monitoring it. What is unusual is not the location. It is the structure of this particular sequence, and specifically the fact that it produced 2 events of identical size 4 days apart inside a block bounded by 3 mapped active faults. Those 3 faults are not lines on a diagram. The Dillar Fault, the Granada Fault, and the Belisena Alhendine Fault are physical structures, traced in the field and in subsurface data, each of them demonstrably active during the Quaternary, each of them oriented to accommodate the extension pulling the basin apart. They are the edges of the box, and the question that everything now turns on is what exactly is moving inside it. Part 6. The 2 possibilities. There are 2 broad explanations for what happened on Tuesday morning, and they lead to very different futures. I am going to give you both of them properly, and then I am going to tell you which one I think is more likely, because I do not think it is honest to lay out 2 options and then lean on the scarier one for effect. The first explanation is the simpler one. On the 14th of August, a patch of a shallow normal fault beneath the Alhendine area ruptured. Not the whole fault, a patch. Faults are not doors that open all at once. They are surfaces, sometimes tens of kilometers across. And an earthquake is a rupture that begins at a point, spreads across some portion of that surface, and then stops. A magnitude 4.8 on a shallow crustal fault corresponds to a rupture patch somewhere in the region of a couple of kilometers across. Small, a fingernail on the scale of the structure. That rupture released the stress on the patch it broke, and in doing so it loaded the rock immediately adjacent to it. Think of tearing a sheet of paper partway across. The torn section is now relieved of tension. The intact fibers right at the tip of the tear are carrying everything the torn section used to carry, and they are carrying it concentrated. 3 days later, under that concentration, one of those adjacent patches failed. And because it was a similar patch of a similar structure carrying a similar accumulated stress, it produced a similar earthquake. Magnitude 4.8. Its own rupture then loaded its own neighbours, which is what produced the 3.9, the 4.2, and the 4.0 over the following 2 hours. Under this explanation, everything that has happened is one fault system failing in stages. Nothing new has been introduced. It is a single structure working through its accumulated stress in a lumpy, uneven way, instead of in one clean release. I think this is the more probable explanation, and I want to say so plainly. It requires nothing exotic. Sequences that fail in multiple comparable events instead of one dominant one have a name. Seismologists sometimes call them doublets, or multiplets, or simply swarm-like sequences, and they are well documented, particularly in extensional settings with shallow, structurally complex fault networks, which is exactly what the Granada Basin is, and it makes a specific prediction that can be tested. If this is one fault volume, then when you locate all 432 of those earthquakes precisely enough, they will collapse onto one compact, coherent plane, a single surface, with a single orientation, matching one of the 2 planes on those beach ball diagrams. There is a second diagnostic that comes out of the same catalogue, and it is worth knowing because it is one of the few things seismologists can compute while a sequence is still running. In any population of earthquakes, small events vastly outnumber large ones, and the ratio between them is remarkably consistent. Drop 1 magnitude unit, and you get roughly 10 times as many events. The number that describes that ratio has a name, and it is measurable, and it is not identical everywhere. Sequences that are dominated by one big rupture tend to have a lower value, relatively more large events compared to small ones. Swarm-like sequences, especially in extensional and geothermal settings, tend to have a higher one, a catalogue that is overwhelmingly small events with comparatively few big ones. 432 located events, of which only 9 reached magnitude 3, is a very bottom-heavy distribution. That is not conclusive on its own, and I do not want to oversell a statistic computed on 5 days of data. But it is another line of evidence pointing at the same conclusion the mechanisms point at. This is behaving less like one great release, and more like a complicated volume of shallow crust failing repeatedly in a lot of small pieces. Now the second explanation. When a fault ruptures, it does not only load the rock at the edges of its own rupture patch, it changes the stress field for kilometers around, and it does so in a way that has structure to it. Some parts of the surrounding crust are pushed further from failure, other parts are pushed closer to it. This is called Coulomb stress transfer, and the underlying idea is not complicated. Whether a fault slips depends on the balance between the shear stress trying to slide it and the friction holding it in place, and friction depends on how hard the 2 sides are being clamped together. An earthquake nearby can increase the shear stress on a neighbouring fault, or it can unclamp it by reducing the pressure squeezing it shut, or both. Either way, the neighbour gets closer to its own failure threshold. The amounts involved are tiny. Stress changes from a moderate earthquake on faults a few kilometres away are typically measured in fractions of a bar, a small fraction of atmospheric pressure against the enormous stresses locked into the crust at depth. This is not one earthquake shoving another one into existence, and that is the crucial thing to understand about it, because it is where the concept usually gets mangled. Stress transfer does not create an earthquake out of nothing. It advances the clock on an earthquake that was already coming. If a neighbouring fault was 200 years from failure, a fraction of a bar does nothing measurable. If it was already loaded to within a hair of its threshold, if it was going to break this decade regardless, then a small nudge can be the difference between breaking next year and breaking on Tuesday. If that is what happened here, then the earthquake on the 14th of August pushed a nearby structure over a line it was already approaching, and this explanation also makes a testable prediction, and it is a different one. If a second structure is involved, then precisely located hypocenters will not collapse onto one plane. They will form 2 distinct planes, or they will begin extending along the strike of one of the mapped bounding faults, a line of seismicity marching in a direction, rather than a cloud sitting still. I covered a version of this same structural question a week ago, in the video on the swarm that tore through the central San Andreas. 59 earthquakes in 6 days, on a completely different kind of fault, in a completely different tectonic setting, and the whole story was the difference between a swarm and a main shock aftershock sequence. Different continent, different mechanism, same question. Is this one thing failing repeatedly, or several things talking to each other? And fault-to-fault influence is not a fringe idea. It is standard, mainstream earthquake physics, worked on for decades, and there is a substantial literature on major fault systems whose rupture histories appear to have influenced one another. I have gone through the case for partial synchronization between the northern San Andreas and the Cascadia subduction zone on this channel before, two of the most consequential faults in North America, apparently keeping time with each other over thousands of years. That work is contested in its details and taken seriously in its outlines, and nobody in that argument thinks stress transfer between neighbouring faults is controversial. But I need to hammer the caveat here, because this is precisely the point where people run off the edge of the map. Even if the second explanation is correct, even if a neighbouring structure has been brought into this sequence, what is being described is a small patch of a nearby fault failing. That is all. It is not a rupture propagating along the Granada fault. It is not the Dilla fault unzipping. There is no evidence for anything like that. The Institute has not suggested anything like that, and nothing in the current data points that way. The difference between the two explanations, in terms of what has already happened, is a few kilometres of geometry. Where the difference actually matters is in what it implies about what could happen next. And to get at that, you need to know which one it is. Right now, nobody does. Both explanations are consistent with every observation made so far. Two identical magnitudes, normal mechanisms, a compact epicentral area, a cluster of aftershocks distributed across a few kilometres. All of that fits either story. And there is a third question underneath both of them that I think is the genuinely uncomfortable one. Which event is actually controlling this sequence now? For 3 days, that had an obvious answer. The 14th of August was the main shock and everything else was a response to it. From Tuesday morning onward, the honest answer is that nobody knows. Is the 18th of August a very large aftershock of the 14th, still part of one process that started 4 days earlier? Or is it a separate earthquake that happens to have occurred in the same place, with its own aftershock sequence, which is now superimposed on the tail of the first one? Those are different pictures, and they imply different things about how much stress remains in that volume. Under the first picture, the total budget is being drawn down. Under the second, you have two overlapping processes and no clean way to tell whose aftershocks you are counting. The vocabulary of main shocks and aftershocks assumes a hierarchy. Take the hierarchy away, and the vocabulary stops describing anything, which is why the next thing to watch is not a number on a seismometer. Part 7. The map matters more than the magnitude. The next earthquake map will tell us more than the next magnitude number. I have said versions of that sentence on this channel before, and I mean it more here than almost anywhere, because in this specific case there is a clean, well-defined observation that separates the two explanations, and it is coming. To understand why, you need to know how earthquakes get located and why the routine locations are not good enough for this. When an earthquake happens, seismic waves radiate outward at different speeds. The compressional wave arrives first, the shear wave arrives later, and the gap between them at any given station is proportional to how far that station is from the source. Collect those arrival times from several stations, run them through a model of how seismic velocity varies with depth, and you can solve for a position and an origin time. That works, and it is what produces the locations you see in a catalogue within minutes of an event. But it carries error, and the error is not small. Horizontal position might be good to a kilometre or two. Depth is much worse, because depth is the parameter the geometry constrains least well. It is the hardest thing to pin down, and the most important thing for this question. The error comes mostly from the velocity model. Real crust is heterogeneous. It has faults and sediment basins and intrusions and layers that the smooth mathematical model does not capture, so every arrival time carries a small systematic bias from the ground it happened to travel through. Here is the clever part, and it is the reason this question is answerable at all. If two earthquakes occur close together, the waves from both of them travel almost the same path to any given station, which means they pick up almost the same error. So if you compare the arrival times of the two events at the same station, rather than trying to locate each one on its own, most of that error cancels out. Do that across hundreds of event pairs, and you get relative relocation. You may still be slightly uncertain about where the whole cloud sits in absolute terms, but the internal structure of the cloud sharpens enormously. Fuzzy blobs that looked like a shapeless cluster resolve into planes, lines, and surfaces. Faults that were invisible in the routine catalogue appear as sheets of hypocenters, sometimes only tens of meters thick. That is the technique that will settle this. And there is a limiting factor. You need instruments close to the source, because near field stations are what constrain depth, which is why one particular detail in the Institute's bulletin matters more than anything else in it. 2 portable seismic stations have been deployed into the epicentral area, specifically to improve the location and characterization of this sequence. That is not a routine action. That is a monitoring agency deciding that the standard network is not sufficient to answer the question it now has, and physically driving instruments into the valley to get better data. The standing network was already good. Within roughly 50 kilometers of the epicentral zone, there are 52 permanent seismic sensors, 2 velocity sensors, 30 acceleration sensors, and 20 low-cost accelerographs supplementing the acceleration network. On top of that, 7 stations shared with the Andalusian Institute of Geophysics. The nearest permanent accelerographs sit at Armilla, Churiana de la Vega, and Dilla, roughly 3 and 5 kilometers from the epicenters. I want to put that in perspective, because it is genuinely unusual. Most earthquake sequences of this size anywhere on Earth are watched from much further away. A magnitude 4.8 in a sparsely instrumented part of the world might have its nearest station 100 kilometers off, and its depth might be uncertain by 10 kilometers or more, which would make the question this video is asking completely unanswerable. Here, the closest instruments are 3 kilometers from the source, and there are dozens of them, and now there are 2 more that were carried in by hand. This is one of the best instrumented moderate earthquake sequences in the world right now. It is worth pausing on what that density buys, because it is not only about location precision. 30 acceleration sensors and 20 supplementary accelerographs inside a 50-kilometer radius means the ground motion itself is being sampled at dozens of points across a landscape with wildly varying geology. That is how you learn that one town shook at twice the intensity of its neighbour, and it is how engineers eventually work out which building types in which soil conditions took the most punishment. Those low-cost accelerographs are worth a specific mention, because they represent a real shift in how seismic monitoring works. Traditional research-grade instruments are expensive enough that networks are always sparse. Cheap, robust sensors deployed in large numbers trade some sensitivity for enormous gains in spatial coverage, and for measuring strong shaking in populated areas, coverage beats sensitivity almost every time. You do not need a delicate instrument to record a quarter of a gravity. You need a lot of instruments, spread across a lot of different ground. That is the network that recorded Tuesday morning, and it is the reason the numbers in the next part of this video exist at all. There is a timescale on this, and I want to set expectations honestly, because watch for the map is only useful if you know roughly when to watch. Relative relocation is not something you run in an afternoon. It needs a substantial catalogue. The more event pairs, the better the cancellation of error, and it needs waveforms from the portable stations, which only started recording after they were installed. Those instruments will capture the ongoing seismicity, not the earthquakes that already happened, which means the highest resolution picture will come from events recorded from here onward. In practice, the kind of relocated catalogue that would settle this question tends to appear over days to weeks, not hours, and often in a technical report or a scientific paper rather than a press release, which is a slightly deflating thing to say in a video about an event unfolding right now, but it is the truth. The most important information about this sequence will arrive quietly, in a figure, after the news cycle has moved on. So the test is clean, and I want you to hold on to it in exactly these terms. If the relocated hypocenters collapse onto one compact plane, a single surface, a single orientation, then this is one fault volume, still working through its stress in stages. Explanation 1. If they resolve into separate planes, or begin extending along the strike of one of the mapped bounding faults, then a second structure has been drawn into the sequence. Explanation 2. And the reason this is worth caring about rather than being an academic distinction comes down to dimensions. The maximum magnitude a fault can produce is governed largely by how much surface area can rupture at once, which is governed by the fault's length and depth extent. A small structure in the middle of the basin has one ceiling. One of the mapped bounding faults, a mapped, traced, quaternary active structure, has a different and higher one. Knowing which one you're dealing with tells you which ceiling is the relevant one. It also changes what the end of this sequence would even look like. If it is one patch failing in stages, the sequence ends when that patch runs out of unbroken area. If a second structure is involved, then over is a much harder thing to declare, because you now have two systems talking to each other and no clean way to know when the conversation has finished. There is a third thing the geometry would tell you, and it is the one that matters most for the people in those apartment blocks: depth. If the relocated hypercenters cluster at 2 or 3 kilometers, the shaking will keep being brutally efficient at delivering energy into buildings directly above, regardless of magnitude. If they sit deeper, at 8 or 9 kilometers, the same magnitudes will feel meaningfully less violent at the surface. Every located event in this sequence so far has been shallower than 10 kilometers, which is a wide band. Where in that band this is actually happening is not yet resolved, and it is the difference between a magnitude 4 that rattles windows and a magnitude 4 that cracks a pillar. And here is what relocation will not do, stated plainly, so nobody walks away with the wrong idea. It will not predict the next earthquake. It will not produce a date. It will not tell anybody in Las Caballas whether it is safe to go home. It is a diagnostic tool that tells you what you are looking at, not what it is going to do, which is the frustrating part. Because while seismologists wait for a map that will explain the geometry of what is happening, the people living directly on top of it do not get to wait for anything at all. Part 8. 24% of gravity. Forget the magnitude for a moment. I want to show you the number that actually decides whether a building survives. Magnitude describes the earthquake. It is a property of the rupture, computed from the energy radiated at the source, and it is the same number whether you're standing on top of it or reading about it in another country. It is a useful number for comparing earthquakes to each other, and it is very nearly useless for working out what happened to a specific wall. What a building experiences is acceleration. How hard and how fast the ground underneath it changed direction. Engineers measure that as a fraction of g, the acceleration due to gravity, which is what you feel pinning you to your chair right now. A ground acceleration of 1g means the ground is being thrown sideways as hard as gravity pulls you downward. Buildings are designed with enormous strength against vertical load because gravity is always on and every structure has been fighting it since it was built. They are much less naturally resistant to being shoved sideways because sideways is a load that only arrives during earthquakes and high winds. So when you see a ground acceleration expressed as a percentage of g, what you are reading is, how hard was this building shoved sideways, relative to how hard gravity is pulling it down. The instrument doing this work in Granada is an accelerograph at our Miller, roughly 3 kilometers from the epicenters. 3 kilometers from a source that is only a few kilometers deep is about as close as you ever get to a rupture with a permanent instrument. Here is what it recorded. On the 14th of August, from the magnitude 4.8, peak ground acceleration of 0.24 g, 24% of gravity. The shake map analysis put the maximum at 24.6% of g, with a peak ground velocity of 8.2 centimeters per second. On the 18th of August, from the second magnitude 4.8, peak ground acceleration of 0.226 g, 22.6% of gravity, with a peak ground velocity of 14.7 centimeters per second. Now here is the number that puts both of those in context, and it is the single most important comparison in this entire video. According to the seismic hazard map produced by the Institute in 2012 and revised in 2015, the design peak acceleration for the municipality of Alhambra, for a return period of 475 years, is 0.23 g. Read that against the two measurements again. 0.24 g, observed. 0.226 g, observed. Against a 475-year design value of 0.23 g. Two moderate earthquakes, 4 days apart, delivered ground acceleration at essentially the level that Spanish seismic hazard mapping associates with a 475-year event at that location, twice, in 4 days. I want to be very careful about what that does and does not mean, because it is the kind of number that gets weaponized, and the wrong reading of it is genuinely misleading. It does not mean the hazard map is broken. That 475-year figure is a probabilistic value. It describes the level of shaking that has roughly a 10% chance of being exceeded over 50 years at a given site, integrated across every earthquake source in the region and every magnitude those sources can produce. It is a design target for building codes, not a prediction of how often the ground will move that hard at one particular accelerograph, and it does not mean that a 475-year earthquake has occurred. It has not. A magnitude 4.8 is a common earthquake in this basin. What is uncommon is being 3 kilometers from one that is only a couple of kilometers deep. That is the actual lesson, and it is one of the most useful things anybody can take from this whole event. Shallow depth and near-field distance can make a modest earthquake deliver ground motion at the surface that you would normally associate with a much rarer one. The magnitude was ordinary, the geometry was not. Which is precisely why the Alhambra was evacuated over a magnitude 4.8 and why 6 apartment blocks were cleared. The people making those calls were not reading the magnitude, they were reading the accelerograph. There is a practical dimension to that design number that is worth spelling out, because it is where the abstraction touches actual buildings. A design acceleration is what goes into the building code. It is the load a new structure in that municipality is required to be able to withstand without collapsing, and it feeds into how much steel goes into a column, how walls are tied to floors, how a frame is detailed at its joints, which means every building in Alhambra constructed since the current code took effect has, at least on paper, been engineered for shaking around this level. That is genuinely reassuring, and it is a large part of why 3 minor injuries is the casualty figure rather than something far worse. It is also why the age of a building is the single most useful thing to know about it here. A structure completed in 2018 was designed for this. A structure completed in 1968 was designed for gravity, wind, and whatever the builder's judgment supplied. Those 2 buildings can stand next to each other on the same street, on the same soil, and experience the same earthquake in completely different ways. The shake map analysis gives a sense of how widely the strong motion was spread. For both magnitude 4.8 events, the area nearest the epicenter saw estimated accelerations above 10% of gravity and velocities above 5 centimeters per second, with the peaks at Armilla. 10% of gravity is not a footnote either. It is comfortably enough to crack plaster and dislodge masonry on an older building. And there is a second thing hiding in those numbers, which almost nobody has picked up on, and which I think is the strangest single detail in this sequence. Look at the 2 events again. Same magnitude, same station, and yet acceleration slightly down, from 0.24 to 0.226. Velocity almost doubled, from 8.2 centimeters per second to 14.7. That is a 79% increase in peak ground velocity between 2 earthquakes that the moment tensor says were the same size, recorded on the same instrument, in the same ground. Acceleration and velocity are not interchangeable. Acceleration is dominated by high-frequency energy, the sharp, rattling content that shakes small, stiff things. Velocity carries the lower-frequency energy, the long, rolling motion that shifts large masses. A divergence like this means the 2 ruptures radiated genuinely different frequency content. There are a few things that could do that. The direction the rupture propagated relative to the station, which can focus energy the way a moving siren compresses sound waves ahead of it. A difference in depth, since shallower ruptures in softer material generate more low-frequency motion. A difference in how fast the rupture ran or how smoothly it slipped. The point is simple and it is important. The 2 magnitude 4.8s were the same size and they were not the same earthquake. Something about the second rupture was different from the first, and that difference showed up in what the ground did. And here is why the velocity number is the one that should worry you rather than the acceleration number. For masonry buildings and mid-rise structures, the exact building stock of the Vega de Granada, peak ground velocity is a better predictor of damage than peak ground acceleration. High-frequency rattling is hard on brittle finishes and contents. Low-frequency rolling motion is what pushes whole walls and whole floors sideways, which means that by the metric that best predicts structural damage, the second earthquake was substantially worse than the first, even though its headline acceleration number was slightly lower, and it arrived at buildings that had already taken the first one. Part 9. Buildings do not reset. A building does not go back to how it was. That sentence sounds obvious, and it is the thing that almost everybody gets wrong when they think about earthquake sequences, because the mental model most people carry is that a building either survives an earthquake or it does not. It stands, or it falls. If it is still standing afterward, it passed. That is not how structures work. Follow a single element through Tuesday. Take a reinforced concrete pillar in one of those Las Gabias apartment blocks, an ordinary column, doing an ordinary job carrying the weight of the floors above it. On the night of the 14th of August, it was shaken sideways at 24% of gravity for several seconds. It did not fail, it flexed, and the concrete on the tension side of that flex developed hairline cracks. Cracks too fine to see without looking for them, some of them invisible under paint. That pillar is still holding the building up. It has also permanently changed. Concrete carries compression well and tension poorly, and once it cracks in tension, that portion of the section stops contributing. The steel reinforcement takes over, which is what it is there for, but the column as a whole is now slightly less stiff than it was, and slightly less able to absorb the next cycle before something more serious happens. Its capacity has been drawn down. Now shake it again on Tuesday morning at 22.6% of gravity, with nearly double the ground velocity. Then again 15 minutes later. Then again 57 minutes after that. Then again an hour after that. The same process runs through every element in the building. Mortar joints in masonry walls that opened slightly and did not fully close. Ties between a wall and the floor slab that were loosened rather than broken. Infill panels, the non-structural walls that fill the gaps in a frame, that cracked around their edges and are now free to move independently, which is exactly the condition under which they fall out of the frame entirely. This is what engineers mean by cumulative damage. Repeated moderate loading can do what a single larger event would not, because each cycle starts from a lower baseline than the one before it. The structure is not being tested against its original design capacity. It is being tested against whatever it has left. I have talked about this problem before on this channel in a completely different setting. The videos at the start of this month about the Brady seismic crisis under the Bay of Naples, where the ground has been rising and shaking for years and the building stock in the towns above it is heavily masonry. Much of it old, a lot of it built before anybody was designing for seismic loads at all. Different geology entirely, volcanic there, tectonic here. But the structural problem is identical, and it is the reason the authorities in both places behave in a way that looks disproportionate to a single magnitude number. The Vega de Granada has that same profile. A significant share of the building stock in these towns is older unreinforced or lightly reinforced masonry, and masonry is the material that suffers most under repeated shaking. It is strong in compression and weak in tension. It has no ductility to speak of, and once a crack pattern is established, it concentrates every subsequent load into the same weakened lines, which is precisely the class of structure where peak ground velocity, the number that nearly doubled between the two earthquakes, is the controlling damage parameter. There are two specific vulnerabilities in Mediterranean apartment blocks that are worth naming, because they are why engineers went straight to the pillars. The first is the soft story. An enormous number of residential blocks across southern Europe have a ground floor that is mostly open, garages, shop fronts, an entrance lobby, sitting under several floors of solid, heavily walled apartments. Structurally, that is a stiff, heavy box balanced on a set of relatively slender columns. When the ground moves sideways, almost all of the deformation concentrates in that open ground floor because it is the only part of the building flexible enough to absorb it. The columns on that level take everything. It is the single most common cause of collapse in moderate earthquakes worldwide, and it is exactly why the phrase in the reports is the condition of some pillars requires more detailed analysis, rather than cracks were found in the walls. The second is pounding. Urban blocks are often built right up against their neighbours with only a token gap. Buildings of different heights and different stiffnesses sway at different rates, and if the gap is too narrow, they collide during strong shaking, repeatedly at floor slab level, which is where the impact does the most harm. 4 earthquakes above magnitude 3.9 in 2 hours is a lot of opportunities for adjacent buildings to hit each other. Neither of those is visible from the street. Both are the kind of thing an engineer finds by getting into the ground floor with a torch and looking at where columns meet slabs. Now, there is an apparent contradiction in the official record that I want to resolve, because people have noticed it and it looks suspicious if you do not understand it. The Institute's damage characterization, as of the 18th of August, is that these earthquakes have produced non-structural damage and falling objects in various constructions within the epicentral zone. Non-structural damage. That is the official seismological assessment, and yet municipal engineers ordered 371 homes evacuated. Those two statements look like they cannot both be true, and they are both true because they are answering different questions. The Institute is compiling a damage record, a systematic, evidence-based catalogue of what these earthquakes demonstrably did, which feeds into intensity assignments and eventually into hazard models. It is a scientific record, and it is conservative by design. The municipal engineers are making a precautionary decision under uncertainty before assessment is complete. Their question is not, what damage has been documented? Their question is, can I certify that these buildings are safe to sleep in tonight? Those are completely different standards of proof. And notice what nobody has said. Nobody has said these buildings are going to collapse. No official has claimed that. The inspections carried out so far did not find major structural damage. What they found was that the condition of some pillars requires more detailed analysis before residents can go back. That is the whole point. The problem is not that the buildings are known to be dangerous. The problem is that their remaining capacity is currently unknown, and after 2 earthquakes at 20+% of gravity, unknown is not a state anybody is willing to let 600 people sleep in. Engineers get more cautious with each repetition, not less, and the reason is straightforward. Every cycle of shaking widens the uncertainty on what a damaged structure can still take. After 1 earthquake, you can inspect and estimate. After 5 in 4 days, with more possibly coming, the honest answer is that you need to open things up and look properly, which is how 6 apartment blocks in one town ended up empty on a Tuesday night in August. Part 10. 600 people and a municipal theatre. 371 homes, 6 apartment blocks, roughly 600 people, one town. Las Caballas sits on the flat of the Vega, a few kilometres from the epicenters, and by Tuesday evening it had become the clearest measure of what this sequence has actually cost. The reason those people are out is specific and worth repeating precisely, because it has been reported loosely. Inspections carried out so far had not detected major structural damage. What they detected was that the condition of some pillars requires more detailed analysis before residents can return. The evacuation was preventive. The town opened its municipal theatre as temporary accommodation for residents who had no alternative housing. I find that detail more affecting than any of the seismological numbers in this video. A municipal theatre, rows of seats, a stage, a foyer, and several hundred people who cannot go home because nobody can yet certify the pillars in their building. It is the least cinematic possible image of an earthquake, and it is what most earthquake displacement actually looks like. Not rubble and searchlights, but a public building with the lights on, and families working out where to put their things. Around them, the rest of the response. The Alhambra was evacuated. The Nasrid palaces and the Alcazaba cleared of visitors, and the monument closed. That is the image that travelled around the world, and it deserves a moment. This is a complex that has stood since the 13th and 14th centuries, on a ridge above the city, through every earthquake this basin has produced in 700 years, including 1884. It is one of the most visited monuments in Spain, and on Tuesday morning it was emptied and shut because of a magnitude 4.8. And closing it is not a small decision. The Alhambra is among the most visited monuments in Europe, with visitor numbers in the millions annually, and timed entry tickets that sell out months ahead. Shutting it in the middle of August, peak season, means turning away thousands of people who planned their trip around it, and it means the institution that runs it decided that the risk of a masonry fall inside a 700-year-old palace complex outweighed all of that. Nobody makes that call over a tremor. They made it over an accelerograph reading. Shopping centres across the metropolitan area were evacuated. Heritage buildings were inspected. The Granada metro slowed to 30 kilometres an hour. Emergency line 112 in Andalusia logged more than 50 calls reporting collapses and cracking. 3 people were injured, all minor, one of them a minor taken to hospital. The metro decision deserves a sentence of its own, because it shows how far the caution extends. A light rail line runs on track that is aligned to millimetre tolerances, over ground that has just been shaken 4 times. Nobody expects the track to have moved, but settlement in the ballast, a slight shift at a joint, a displaced fixing, none of those are visible at speed, and all of them are survivable at 30 kilometres an hour. So they slowed the trains and started inspecting, and they will keep doing it until somebody is confident enough to sign the line back to full speed. That is the texture of the whole response, not panic, not evacuation of the city. A long list of institutions each deciding, independently, that they would rather be slow than certain. The thing nobody in that theatre has been given is a date. Structural assessment of 6 apartment blocks is not a same-day process. It means intrusive inspection, opening up finishes to see the actual condition of columns and connections, sometimes coring concrete to test its strength, sometimes surveying the frame for permanent lean. Then an engineer has to put their name on a document saying the building is safe, or safe with repairs, or not safe. And every one of those assessments has to be redone if the ground moves significantly again, which in a sequence that produced 4 events above magnitude 3.9 in 2 hours on Tuesday is not a remote possibility. That is the loop those 600 people are stuck inside. There are further reports that I want to attribute carefully rather than assert, that vulnerable residents of a care facility, some 70-odd people, were relocated after damage was found, that a health centre was taken out of service, that roads were closed, that vehicles were struck by falling masonry. Those have circulated widely in coverage of the event, and they are consistent with everything else in the picture, but they are not in the material I have been able to verify directly against a primary source. So I am flagging them as reported rather than confirmed, and you should hold them a little more loosely than the numbers I have given you from the Institute's bulletin. Now here is the reframe that I think actually matters, and it is the thing this whole act has been building toward. The risk that deserves attention in Granada over the next week is not a hypothetical magnitude 6. It is a partial failure, a pillar, a stair core, a section of wall, a balcony, in an already damaged building during the next magnitude 4. That is a far less dramatic sentence than the one people want to hear. It is also the one supported by every piece of evidence available. The buildings have been loaded twice at or above their design acceleration. Their remaining capacity is unquantified, and the sequence is still producing magnitude 4s, and all of it, every displaced family, every closed monument, every slowed train, traces directly back to the structural fact this video started with. A single magnitude 4.8 is a damage event. You inspect, you repair, you move on. 2 magnitude 4.8s, 4 days apart, on the same ground, is a loading problem, and a loading problem is a fundamentally different thing to manage. That is the surface consequence of the sequence losing its dominant event. The question the seismologists are asking about fault planes, and the question the engineers are asking about pillars are the same question, wearing different clothes. And the engineering verdict on those pillars has not been issued. Until it is, nobody can say whether Tuesday's evacuation was an abundance of caution or the bare minimum. Part 11. Granada has run this experiment before. December 2020. 10 kilometres northwest of where the current earthquakes are happening, in the same basin, on the same kind of structures, this valley did something remarkably similar, and it is the single most useful piece of evidence available for reading what is happening now. The series is known by the towns at its centre, Santa Fe and Atafe. It began in December of 2020 and it ran until August of 2021. Here is what it produced. More than 3,000 shallow earthquakes, 6 events between magnitude 4 and magnitude 5, with a maximum of magnitude 4.5. Maximum observed intensities of 5 to 6, the same intensity band as the current sequence. A maximum recorded acceleration of 0.195 g, and a duration of roughly 8 months. 8 months. That is the number that should reset everybody's expectations about how long this kind of thing lasts. Not 8 days, not 3 weeks. 8 months of a valley being shaken repeatedly, with multiple magnitude 4 events scattered through it, with damage, with evacuations, with people who stopped sleeping properly for most of a year. I want to dwell on what 8 months of that is actually like, because the statistics flatten it into nothing. The Santa Fe and Atafe sequence began in the winter, in the middle of a pandemic, and for weeks at a time the ground under those towns produced felt earthquakes almost daily. Not damaging ones, mostly, just constant. People slept in cars, schools were inspected and reopened and inspected again. Buildings were checked, cleared, and then shaken again the following week, which meant the checks had to be redone. The exhausting part of a sequence like that is not any single earthquake. It is the impossibility of deciding that it is over. Every quiet week raises the question of whether it has finally stopped, and every new tremor answers it. That is a genuinely corrosive thing to live inside, and it does not show up in a catalogue of magnitudes, and it produced 6 events between magnitude 4 and 5 over that span, which is worth holding next to the current sequence, where 4 events of magnitude 3.9 and above arrived inside 2 hours on a single Tuesday morning. And here is how it ended. It did not culminate in a large earthquake. It decayed, it ran out of energy, the events got smaller and less frequent, and eventually it stopped being a sequence and went back to being background seismicity. That is the local base rate, and it is worth far more than any global statistic because it comes from the same crust, the same fault network, the same stress field 10 kilometers away. Now let me do the comparison honestly, in both directions, because it does not all point the same way. The current sequence has already exceeded Santa Fe Atafe on the measures that describe severity. Maximum magnitude 4.8 against 4.5. Maximum acceleration 0.24 g against 0.195 g. And it has done that in 5 days, where the earlier series took 8 months to reach its ceiling. But the current sequence is far behind on volume. 432 located events against more than 3,000. Whatever the Alhambra sequence is doing, it is not yet in the same category for sheer productivity. So the comparison cuts both ways, harder, faster, and much shorter so far. There is one more comparison in those numbers that I find genuinely useful. Maximum acceleration in the earlier sequence, 0.195 g. Maximum acceleration in this one, 0.24 g. The design value for the municipality, 0.23 g. So Santa Fe Atafe, across 8 months and 3,000 earthquakes, never quite reached the 475-year design acceleration. The Alhambra sequence cleared it on its first night and matched it again 4 days later. That is not a prediction of anything. It is a measure of how much harder this sequence is hitting the surface, and it explains why the response this time has been faster and more aggressive than the response in 2021. The evacuations came within hours, not weeks. What the precedent establishes is that multi-month sequences with repeated magnitude 4 events are a known behaviour of the Granada Basin. Not unprecedented, not anomalous. Something this crust does, documented in detail, within living memory, and monitored by the same institution with the same instruments. What the precedent does not establish is what will happen next. A base rate is not a forecast. Santa Fe Atafe decayed. That does not mean Alhambra will. The most it does is tell you which outcomes are ordinary for this place, and a long grinding sequence that fades out without a large earthquake is very clearly one of them. And there is a detail in that earlier sequence that connects directly to the question this video keeps circling. Santa Fe Atafe also raised the one fault or several problem. A shallow, extensional, structurally complicated basin does not tend to fail on one clean surface. It fails across a network of small interlocking structures, which is exactly why these sequences produce thousands of small events and multiple moderate ones rather than one clean main shock. If that is the character of this crust, and 3,000 events over 8 months is a strong argument that it is, then the Alhambra sequence producing 2 co-equal 4.8s is less an anomaly than a signature. That is a genuinely important reframing, and I want to make sure it lands. Everything in this video so far has treated the second magnitude 4.8 as a departure from normal behaviour, because measured against the standard main shock aftershock model, it is. But the standard model was built largely on large earthquakes on major well-organised faults, long continuous structures that store enormous stress and release it in one dominant rupture. A shallow extensional basin crisscrossed by short, segmented, intersecting normal faults does not work that way. There is no single large structure to dominate the sequence. There are lots of small ones, none of them capable of a huge earthquake on its own, all of them capable of loading each other. Under those conditions, a sequence that produces several comparable moderate events instead of one clearly dominant one is not a warning sign. It is what that kind of crust does, which does not make it harmless. The buildings do not care about the tectonic explanation, but it does change how alarming it should be, and it is the strongest argument available for the first of the two hypotheses, or at least for a version of it in which one fault volume means a small tangled network of related structures rather than a single clean plane. The relocation map will show which, and if the earlier sequence is any guide, the answer will look messy. 8 months is a long time to live above a fault that keeps clearing its throat. But it is not the worst thing this basin has ever done, and to understand why anybody in Granada takes a magnitude 4.8 seriously, You have to go back 142 years. Part 12, 1884. On the 25th of December, 1884, an earthquake struck the province of Granada, centred near a village called Arenas del Rey. It reached a maximum intensity of 9 to 10 on the macroseismic scale. Its magnitude is estimated at around 6.5. It damaged an area of roughly 14,000 square kilometres, and it killed close to 1,000 people. That is the event every Granada earthquake is measured against, whether anybody says so out loud or not. It is why an evacuation order in Las Caballas is followed rather than argued with, and it is why a magnitude 4.8 in this basin generates a response that would look wildly disproportionate somewhere else. Let me give it to you properly, because a number and a death toll do not convey it. It happened at 9 in the evening, on Christmas night, in winter, in a region of mountain villages built almost entirely of stone and mud mortar. The houses were the kind of construction that had worked perfectly well for centuries. Thick walls, heavy roofs, materials from the immediate landscape, and which is close to the worst possible thing to be inside during strong shaking. Rubble masonry has essentially no tensile strength. When the ground moves sideways hard enough, the walls do not flex. They come apart and the roof comes down. Villages across the Alhambra and Jeta valleys were destroyed. Arenas del Rey itself was effectively flattened. It was midwinter in mountain terrain, roads were poor, communications were slow, and survivors spent days outdoors in freezing conditions before organised relief arrived. Some settlements were not reached for over a week. The relief effort became a national event in Spain, and the reconstruction reshaped several of those villages permanently. A number of them were rebuilt on different sites, to different plans. The rupture is most probably attributed to the Ventas de Zafaria fault, which is a normal fault. Same mechanism family as everything happening under Alhambra right now. Extension, hanging wall dropping, different structure, and a very much larger one, but the same physical process. That fault is worth knowing about on its own terms, because it is the clearest illustration of the ceiling question. Ventas de Zafaria is a substantial structure at the margin of the basin system, long enough and deep enough to rupture over a scale that a small intrabasin fault simply cannot reach. It is the difference between a crack in a pane of glass and a crack running the length of a window frame. Both are cracks. Only one of them takes the window out, and the 1884 earthquake is one of the reasons Spain has the seismic monitoring and hazard mapping infrastructure it has. A catastrophe on that scale, in a country that had not experienced one in living memory, generated a national response, scientific commissions, systematic damage surveys, and eventually the institutional machinery whose bulletins this entire video is built on. The 475-year design acceleration for Alhambra exists, in a real sense, because of what happened to Arenas del Rey on Christmas night. There is a version of that event worth thinking about that has nothing to do with the past. Roughly 1.5 million people live in the province of Granada today, most of them concentrated in the metropolitan area, in multi-storey construction of widely varying age and quality, on basin fill that amplifies shaking. The 1884 earthquake happened in a landscape of scattered villages. A comparable rupture in the same region now would encounter something completely different, and that is precisely the scenario Spanish seismic hazard planning is built around. Not because anybody expects it soon, because it is the thing that has to be planned for. Now I want to do the size comparison carefully, because this is exactly the place where a video like this can mislead by omission. The gap between a moment magnitude 4.8 and a magnitude 6.5 is not a bit bigger. Each full step on the magnitude scale is roughly 32 times more radiated energy. 1.7 magnitude units is a factor of approximately 355 times. If the earthquake on Tuesday morning were a single match, 1884 would be a bonfire you could not stand near. And that is only the energy. The rupture area scales up as well, which means the shaking lasts far longer and affects a vastly larger region. Tuesday's earthquake ruptured something on the order of a couple of kilometres across. 1884 ruptured tens of kilometres. So when somebody draws a line from the current sequence to 1884, they are not describing a small escalation. They are describing a completely different class of event on a different structure, requiring a completely different amount of stored strain, and there is nothing in the current data suggesting that is loading. I have said it before in this video and I will keep saying it. The magnitude has not climbed. The mechanisms are consistent with ordinary basin tectonics, and the Institute has not indicated that any of the mapped bounding faults has begun to rupture. There is also a rupture length argument worth walking through, because it makes the ceiling concrete rather than rhetorical. The size of an earthquake is set principally by how much fault surface breaks at once. Roughly speaking, in continental crust, you need something on the order of 10 kilometers of rupture length to reach magnitude 6, and several tens of kilometers to reach magnitude 7. The seismogenic crust in a setting like this is only about 10 to 15 kilometers thick, which caps how deep any rupture can go, so length is the variable that does the work. Apply that to the current sequence. A magnitude 4.8 corresponds to a rupture patch of a kilometer or two. For this sequence to produce a magnitude 6, something would have to break along 10 kilometers or more of continuous fault surface, which requires a continuous fault surface 10 kilometers long to break along, all of it loaded, all of it able to fail in one go. That is the physical reason the identity of the structure matters so much. A short, segmented fault in the middle of the basin cannot do it, no matter how many magnitude 4s it produces. A mapped bounding fault with kilometers of traced length is a different proposition entirely, and Ventas de Zaffaraya, in 1884, demonstrated exactly what that proposition looks like when it is realized. What 1884 does establish is the ceiling. It is proof that this basin, this fault network, this stress regime, can produce an earthquake that kills 1,000 people. Not a model, not an estimate, a historical fact with a date and a body count. And that is exactly why the one fault or two question is not academic. If the current sequence is a small structure in the middle of the basin failing repeatedly, then its maximum possible magnitude is limited by its own modest dimensions. If it has drawn one of the mapped bounding faults into the story, Dila, Granada, Belisena Alhendine, then the relevant ceiling is set by a much larger structure. Nobody is saying that has happened. But that is the reason people want to know. 1884 is not the only entry in this basin's ledger, though, and the rest of the ledger is, in some ways, more informative than the catastrophe. Part 13. The basin's own rhythm. Pull back from the single disaster and look at the whole record, because the pattern is more useful than any one event in it. 1431. An earthquake south of Granada reaching maximum intensity 8 to 9. That is nearly 600 years ago, in a city that was still the capital of the Nasrid Emirate, and it is in the record because the damage was severe enough to be documented and remembered. 1806 and 1807. A seismic series around Pinos Puente, reaching intensity 7 to 8. 1911. Santa Fe, intensity 7 to 8. 1918. Atafe, intensity 7 to 8. 1955. Armilla, a magnitude 5 earthquake, and Armilla is the town where the accelerograph that recorded Tuesday's shaking now sits. 1956. Purchill, another magnitude 5, the following year. Sit with that last pair for a second because it is the closest historical parallel to what is happening right now. 2 magnitude 5 earthquakes, in adjacent parts of the same basin, in consecutive years. Armilla and Purchill are about 10 kilometers apart. Whatever loaded one of them appears to have had something to do with the other, and that is the same question. One structure or two, and did the first one help cause the second? Being asked 70 years ago with a fraction of the instrumentation. Nobody resolved it then. The data did not exist. It went into the catalogue as 2 magnitude 5 events and stayed there. Look at what that list is telling you. Intensity 7 to 8 events in 1806, 1911 and 1918. Magnitude 5 events in 1955 and 1956. A 3,000 event series in 2020 and 2021. And an intensity 9 to 10 catastrophe in 1884. The rhythm is legible. This basin produces damaging moderate earthquakes on a timescale of decades, and it produces genuinely destructive earthquakes on a timescale of centuries. The current sequence sits firmly in the first category. Everything about it, the magnitudes, the intensities, the duration so far, the damage pattern, places it alongside 1911 and 1918 and 2020 rather than alongside 1884. But there is an uncomfortable corollary in that, and I think it is the most honest thing in this video. The decadal events are the ones that keep testing the buildings, and the buildings are what actually kill people. Nobody dies of an earthquake. People die of structures. In 1884, it was rubble masonry village houses on Christmas night. In a modern sequence, it would be a soft-story apartment block, or a stair core that failed, or a facade panel that came off onto a pavement. The events that are too small to make international news are the events that steadily degrade the building stock, and they arrive frequently enough that a place like the Vega de Granada is essentially never in a state where every building is at full capacity. That is the actual hazard here. Not the century-scale catastrophe, which will happen eventually and which nobody can date. The decade-scale grind, which is happening right now, and which is currently at 4 earthquakes above magnitude 3.9 in a single Tuesday morning. There is a further wrinkle in that, and it is the reason building age matters so much in this specific valley. The Vega de Granada urbanized enormously in the second half of the 20th century. The towns that were evacuated on Tuesday were mostly agricultural villages within living memory, and they are now dormitory towns for a metropolitan area. A great deal of that construction went up in the 60s, 70s and 80s, before modern seismic detailing was standard practice in Spain, and a great deal of it went up quickly. So the building stock sitting directly above this sequence is disproportionately from the era with the weakest seismic provisions, on the softest ground, closest to the epicenters. That is not a coincidence, and it is not anybody's failure in particular. It is what happens when a city expands onto its flat land. And notice how far apart the two ends of the historical record are in terms of what they can tell you. 1431 gives you a single line. Something big happened, and it damaged things badly. 2020 and 2021 gives you 3,000 located events, hundreds of moment tensors, and a peak acceleration figure to 3 decimal places. There is one more thing this list makes clear, and it points forward rather than back. Every one of those historical sequences raised the same question this one does. What is moving down there, and is it one thing or several? 1431 could not answer it. 1884 could not answer it. 1911 and 1918 could not answer it. Even 1955 and 1956 with instruments could not resolve the geometry with any confidence. This is the first Granada sequence being read with moment tensors computed within hours, 52 sensors inside 50 kilometers, and portable stations driven into the epicentral zone within days. Whatever the answer turns out to be, we're going to get one, which is more than any previous generation living in that valley ever had. I think that is genuinely worth appreciating, in a story that is otherwise about cracked pillars and displaced families. Somebody standing in a Tafe in 1918 felt the ground move repeatedly for weeks, and had no way whatsoever to know what was underneath them. They could count the shocks, they could look at the damage, and that was the entire toolkit. The idea that you could compute within hours the orientation of a fault plane you have never seen, 6 kilometers below your feet, from the shape of a wiggle on a machine, would have been closer to magic than science. That capability is roughly a human lifetime old, and the specific version of it that will resolve this sequence, high-precision relative relocation, using hundreds of event pairs to cancel out systematic error, is younger still, developed and refined over recent decades and only really practical since dense digital networks and cheap computing arrived together. So this basin has been asking the same question for 600 years, and this is the first time it is being asked by people who can actually answer it. That is the difference between 1431 and now, not the earthquakes, the instruments, and it may explain why so many people are currently seeing 3 different numbers attached to the same earthquake. Part 14. 3 different numbers for one earthquake. 4.7, 4.8, 5.2, 3 numbers, 1 earthquake, and every one of them published by a credible institution. It is the fastest way to make people believe something is being hidden from them, and the explanation is completely mundane. Start with the 2 scales. Local magnitude is the older measurement. It is calculated from the maximum amplitude of the recorded ground motion, corrected for distance. It is fast. It can be computed automatically within a minute or 2 of an event, and it was the workhorse of seismology for most of the 20th century. It also has a known weakness. It depends on the frequency response of the instrument and on the frequency content of the earthquake, which means it can behave oddly for very shallow events, and for large ones it saturates. It stops increasing properly once earthquakes get big. Moment magnitude is derived from the seismic moment, the rigidity of the rock, multiplied by the area that ruptured, multiplied by how far it slipped. It is a physical description of the size of the rupture, rather than a measurement of how big the wiggle was. It does not saturate, it is the standard for anything that matters, and it takes longer to compute because it needs a full waveform inversion. So 4.7 and 4.8 are not a disagreement. 4.7 is what came out fast on the 18th of August. from Spanish domestic reporting drawing on the initial automatic determination. 4.8 is the reviewed moment magnitude, which is the authoritative figure and the one used throughout this video. 5.2 is a determination from a different agency, using different stations at different distances with a different velocity model. And international agencies routinely land a couple of tenths away from national networks, especially for shallow events where the national network has instruments 3 kilometers from the source and the international one has its nearest station several hundred kilometers away. The gap between 4.8 and 5.2 is roughly a factor of 2.8 in radiated energy. That is enough to change a headline. It is not enough to change a single conclusion in this video. Now, the claim that has circulated most widely, that the magnitude was quietly downgraded to prevent panic. The direction of travel kills it. The Institute's number did not go down. It went up, from an initially reported 4.7 to a reviewed moment magnitude of 4.8. If there were an agency somewhere managing public alarm by shaving decimals, it did a strange job of it by revising upward and by publishing a detailed technical bulletin listing every event above magnitude 3.5 with timestamps to the second. Let me deal briskly with the rest, because they come up every time and they deserve honest answers rather than dismissal. Induced seismicity, fracking, deep drilling, reservoir loading. This is a real phenomenon, thoroughly documented, and it is a fair question to ask of any shallow swarm. It does not fit here. Induced events cluster tightly around an injection or extraction point and typically appear at the depth of the operation. These are distributed across a fault-bounded block at depths reaching 10 kilometers, with mechanisms that match the regional extensional stress field exactly. And this basin has been producing this exact behavior for 6 centuries of written record, which is a long time to blame on industrial activity, earthquake weather, lunar triggering, solar and geomagnetic triggering. All of these have been studied repeatedly using large global catalogues. The correlations that turn up are either absent or so small as to be indistinguishable from noise at the magnitudes we are discussing. Tidal stresses from the moon do measurably influence some seismic environments at the margins. That is a real result, but the effect is a whisper against the accumulated stress in a loaded fault, and it has never been shown to be usable for anything predictive. And then the big one, the claim I know is coming because I have been covering the last 2 weeks of global seismicity, that Granada is connected to what has been happening in Indonesia. There is no mechanism, static stress transfer. The process I described earlier, where one rupture loads a neighbouring fault, drops off steeply with distance. At a few kilometres it can matter. At 10,000 kilometres it is not merely small, it is not a meaningful quantity. Dynamic triggering, where the passing surface waves from a large distant earthquake set off local events, is real and documented, but it operates within minutes to hours of the waves arriving, not days later, and it overwhelmingly affects geothermal and volcanic systems where fluids are already close to a critical state. The honest answer is the boring one. The planet has a great many active seismic zones. They are all doing their own thing continuously, and sometimes several of them make news in the same fortnight. That is not a pattern. That is a news cycle. And notice what every one of these alternative explanations is actually trying to do. They are all attempts to answer the same question the moment tensors are answering properly. What is controlling this sequence? The difference is that the beach balls come with data attached. There is one more claim I should handle, because it is the one with the most emotional pull, that the authorities know the buildings are structurally compromised and are downplaying it. The evacuations are the answer to that. If anybody were managing perception, the play would be to tell people the damage is cosmetic and to go home. Instead, 600 people were moved out of 371 homes, a theatre was opened, a world-famous monument was closed at the height of the tourist season, and a metro line was slowed. Those are expensive, visible, disruptive decisions, and every one of them makes the situation look worse rather than better. That is not what suppression looks like. What it looks like is a system doing the boring thing correctly, in public, and being accused of hiding something because the boring thing is not dramatic enough to satisfy the question, which leaves exactly 3 things worth watching. Part 15. What the next map will show. Let me bring this all the way back to where it started, because the whole story compresses into one sentence. For 3 days, this sequence had a main shock. On Tuesday morning, it stopped having one, and the thing that will explain why is a map. One compact plane, or separate planes. That is the test. Hold on to it and everything else in the coming weeks will make sense. So here are the 3 things to watch, and I want them specific enough that you can actually check them, rather than just feel vaguely uneasy. The first is the relocated catalogue. 2 portable seismic stations are now sitting in that valley, recording, for exactly this reason. When their data is combined with the permanent network and the events are relocated relative to one another, the geometry of whatever is down there becomes visible. If the hypocenters collapse onto a single compact surface, this is one fault volume working through its stress in stages, and the story is essentially over as a scientific question. If they resolve into 2 or more distinct planes, or start marching along the strike of one of the mapped bounding faults, then a second structure has been drawn in, and everything about the sequence's possible ceiling has to be reconsidered. The second is the verdict on the pillars in Las Caballas. 6 blocks, 371 homes, 600 people, waiting on a structural assessment that will say return, repair, or condemn. That is the first hard external test of whether the damage from these earthquakes was genuinely non-structural, as currently characterized, or whether 4 events at or near the design acceleration have taken more out of those buildings than anyone can see from the pavement. That second one is the thread I would watch most closely if I lived there, and it is the one least likely to be reported internationally. The seismology will get written up. Whether 600 people got to go home, and how long it took, and what the engineers found when they opened up those columns, is a local story that will play out over weeks in municipal announcements. It is also the only part of this that produces a definitive human answer. The fault plane question may stay ambiguous for a long time, but a building either gets certified, or it does not. And the third is whether a third co-equal shock arrives. The interval between the 2 magnitude 4.8 events was 3 days, 9 hours and 33 minutes. If another one turns up on a comparable timescale, then the main shock and aftershocks framework has stopped describing this sequence in any meaningful way, and the interpretation shifts decisively toward multiple connected ruptures in a segmented fault network. If instead the next several days stay down in the magnitude 2 and 3 range, and the felt reports thin out the way they did between the 15th and the 17th, then this is decaying, and the 2020 and 2021 sequence tells you what that decay can look like, and how long it can take. There is a fourth thing I would watch, quietly, and it is the most diagnostic of all if it happens: migration. Not bigger earthquakes, moving ones. If the epicenters over the coming week begin walking consistently in one direction, a kilometre at a time, along a line rather than filling in a patch, that is the clearest possible signal that stress is propagating along a structure rather than being consumed inside one. Sequences that migrate are telling you something is being loaded ahead of them. So far, the events have been distributed across the block: Alhambra, Churiana de la Vega, Gojar, La Zubia, rather than marching. That is the current picture, and it is a reassuring one. It is also the thing most likely to change first if the situation changes at all. And I want to state the negative observation one final time, because it is the thing most likely to be lost when this story gets repeated. The magnitude did not climb. There is no 4.8, then 5.2, then 5.8. There is no ladder. There is a 4.8, then 3 days of decay, then another 4.8. That is a repetition, and a repetition is not an escalation. It tells you something significant about the structure of the sequence, and it tells you nothing at all about a larger earthquake loading underneath it. Anybody presenting the last 5 days as a countdown is reading something into the data that is not in it. It is worth being clear about what would actually change my assessment so that you can hold me to it. A third magnitude, 4.8 on a similar interval, epicenters migrating steadily along a line, a relocated catalogue showing 2 distinct planes, a step up to magnitude 5.5 or above. Any one of those would be a genuinely different situation from the one described in this video, and I would say so. None of them has happened. What has happened is a change in the internal structure of a sequence, in a basin that has produced sequences like this repeatedly, monitored better than almost anywhere on Earth, with a 142-year-old catastrophe sitting in the background of everybody's thinking. What is genuinely happening in Granada is stranger and quieter than a countdown, and I think it is worth sitting with. A city of 250,000 people is built on the floor of a basin that is slowly pulling itself apart, inside a continent that is being pushed together above a network of small faults that have been doing this for millions of years and will keep doing it long after every building currently standing has been replaced twice over. The valley is not having an emergency. The valley is doing what it does. It just happens to be doing it this week, on a timescale short enough for people to notice, in units nobody chose and on a schedule nobody controls. 4 to 5 millimeters a year. That is the rate at which the pressure behind all of this accumulates, and it has not paused once during any of the last 5 days. It did not accelerate before the 14th of August, and it did not slow down after Tuesday morning. The convergence is constant. Everything else, the swarms, the quiet years, the magnitude 4s, 1884, is just the crust deciding, on its own schedule, when to let some of it go. The Alhambra has stood on its ridge above that valley for 7 centuries of this. It was there for 1431, it was there for 1884, it was there for Armilla in 1955 and Purchill in 1956 and the 3,000 earthquakes of 2020 and 2021. And on Tuesday morning, for the first time in a long while, somebody decided it was safer with nobody inside it. That is the measure of this week, not a magnitude. A door closed on a building that has outlasted every earthquake anybody in that city can name. And the last honest thing I can tell you is the thing nobody wants to hear. Earthquakes cannot be forecast. Not by the Institute, not by anybody. Nobody can tell those 600 people when it will be over, and anybody offering you a date for the next one is selling you something. What we do have is a question with an answer coming. The 2 largest earthquakes of this sequence were separated by 3 days, 9 hours, and 33 minutes. Everything that happens next depends on one thing, and it is not how big the next one is. It is whether there is a third.